Welcome to Energy Vision Global. I'm Mohammad Wakar. In the previous video, I introduced MWD and LWD and discussed their importance in modern drilling operations. In this video, we will explore the MWD system in depth. We will not only understand what components exist inside the tool, but also how the system performs under real downhole conditions. Most importantly, we will connect theory with real field operations so you can understand how MWD supports directional control, drilling optimization, and operational decision making in practical scenarios. Let's go deeper. Imagine you are drilling a deviated well at 11,000 feet measured depth. The bottom hole temperature is around 145 degrees Celsius. The formation is interbedded shale and sand. You are building angle toward a horizontal target that is only 6 feet thick. At this point, even a small directional mistake can take you completely out of the reservoir. At that moment, the only reason you are confident about the well position is because of the MWD tool. MWD is a complete downhole measurement and communication system integrated into the bottom hole assembly. It is positioned close to the drill bit because directional measurements must represent the actual drilling point as accurately as possible. The further the sensor is from the bit, the larger the positional uncertainty becomes. The MWD tool performs three fundamental functions: sensing, processing, and transmitting. Let us begin with sensing. Inside the tool, there is triaxial accelerometer package. These accelerometers measure gravitational force in three perpendicular directions. By resolving the gravity vector, the tool calculates inclination. Inclination defines the angle between the wellbore and the vertical axis. In a vertical well, inclination remains near 0 degrees. During the build section of a directional well, inclination gradually increases. In a horizontal section, inclination stabilizes around 90 degrees. Now consider a real field example. During a build section in a Middle East onshore well, the planned build rate was 3 degrees per 90 feet. However, real-time MWD surveys showed the inclination increasing faster than planned. The dogleg severity was exceeding operational limits. Because the MWD data was available in real time, the directional driller reduced slide duration and adjusted tool face orientation. As a result, excessive curvature was avoided, preventing future drill pipe fatigue issues. That is practical value, not theory. Now let's talk about azimuth. The MWD tool contains triaxial magnetometers that measure Earth's magnetic field components. By combining magnetic field vectors with inclination data, the system calculates azimuth, which defines the compass direction of the well. However, magnetic measurement is not always simple. Consider another real scenario. While drilling a sidetrack from an existing cased well bore, the MWD azimuth readings began fluctuating abnormally. Investigation showed magnetic interference caused by nearby casing strings. The solution was to apply multi-station correction techniques and, in some cases, switch to a gyroscopic survey tool to verify azimuth accuracy. This highlights an important professional understanding. MWD are reliable, but they must be interpreted intelligently. Now, beyond inclination and azimuth, modern MWD systems measure dynamic drilling parameters. This includes shock, axial vibration, lateral vibration, and torsional oscillations such as stick slip. Let me give you a real offshore example. In a deep water well, rate of penetration suddenly dropped despite stable surface parameters. MWD vibration that showed severe torsional stick slip behavior. The bit was repeatedly stopping and accelerating due to formation resistance. Based on MWD vibration feedback, the drilling team optimized weight on bit and rotary speed. Stick slip intensity reduced, bit life improved, and drilling efficiency recovered. Without MWD dynamic data, this issue might have been misinterpreted as poor bit performance, leading to an unnecessary trip. Now, let's move to processing. All raw sensor data is sent to the downhole electronic module. This module acts as a rigidized high-temperature computer. It filters noise, applies calibration factors, compensates for temperature drift, and converts analog signals into digital form. In high-temperature wells above 150 degrees Celsius, electronic reliability becomes critical. That is why MWD tools are rated for specific temperature and pressure limits. Exceeding these limits can result in tool failure. Now comes the communication challenge. There is no fiber optic cable running from surface to the bit in conventional drilling. So how does data travel? The answer is mud pulse telemetry. Inside the MWD tool, there is a pulsar assembly. This pulsar creates controlled pressure fluctuation in the drilling fluid. These fluctuations travel through the mud column inside the drill pipe to the surface. At surface, a standpipe pressure transducer detects these pressure variations. The surface system decodes the pulse sequence into digital data and displays real-time parameters to the directional driller. There are three primary mud pulse methods: positive pulse, negative pulse, and continuous wave systems. Each has advantages depending on well conditions and depth. Now, consider a deep well case example. In a 17,000 foot well, signal strength began weakening due to increased depth and mud density. Pulse detection became difficult because of background pump noise. The surface team adjusted pump stroke smoothness and optimized filtering settings in the decoding software. Signal clarity improved without tripping the tool. That is operational awareness built around MWD understanding. Transmission speed in mud pulse system typically ranges from 1 to 12 bits per second. That may sound extremely slow compared to modern internet speeds. However, directional surveys and critical drilling parameters require only small data packets. continuous streaming of every sensor detail is not necessary for safe directional control. Now let's discuss power. MWD tools commonly use high temperature lithium battery packs. Battery life depends on temperature, transmission frequency, and operational hours. In high temperature wells, battery performance degrades faster. That is why careful runtime planning is essential. Some advanced systems use mud turbines generators. As drilling fluid circulates, it rotates an internal turbine generating electricity. This allows extended operation without battery replacement. However, turbine systems depend on consistent flow rate. In real field practice, loss of circulation can interrupt turbine generated power, which must be considered in well planning. Another professional consideration is tool placement. MWD tools are placed inside non-magnetic drill collars to avoid magnetic interference. If placed incorrectly near magnetic materials, azimuth accuracy suffers. Proper BH design ensures sensor stability, mechanical protection, and measurement reliability. Let's examine a horizontal well case. While drilling a 12,000 feet lateral section, continuous MWD surveys confirmed that inclination remained stable around 90 degrees. However, slight azimuth drift began appearing over several survey stations. Early detection allowed minor tool face correction during sliding intervals. Without MWD, that azimuth drift might have gone unnoticed, eventually causing the well to exit the reservoir window. This is why we say MWD is not just a measuring tool, it is a real-time decision-making system. It informs steering adjustments, prevents excessive dogleg severity, detects harmful vibration, supports bit optimization, and ensures wellbore placement within target boundaries. If we remove MWD from modern drilling, complex wells such as horizontal shale wells, extended reach wells, and multilateral wells becomes nearly impossible to execute safely and economically. So, to summarize today's video, we explore the MWD tool in depth, understanding how it senses, processes, and transmits critical downhole information. We saw how accelerometers and magnetometers work together to guide well direction, how the pulsar communicates data through drilling mud, and how real-time measurements allow engineers to make immediate, informed decisions in the field. Remember, MWD is not just a tool, it is the backbone of directional drilling. It turns the unknown depths of the well into the actionable knowledge, ensuring safety, precision, and efficiency every step of the way. In the next video, we will build on its foundation and dive into directional calculations, including measured depth, true vertical depth, dogleg severity, and survey analysis, all explained with real-world examples to bring the concepts to life. If you find today's video valuable, make sure to like, share, and subscribe to Energy Vision Global, and leave your questions or thoughts in the comments below. Your engagement helps me bring more real-world drilling knowledge straight to you. I'm Muhammad Wakkar, and I will see you in the next video as we continue to unlock the secrets of modern drilling operations.